Hello everyone, welcome again to this video. In the last video we did some good amount of problems on indefinite integration, and on this one we would try to do the same, and at the end I would try to introduce a new concept which is integration by parts. And let us see if we can do some problems of integration of parts in this video, or we might actually integrate it in the next one. But for now we are going to practice a whole lot more of indefinite integration, and I want you to actually pause the video whenever I give you a problem and try it on your own. And if you cannot, please go to the last video and see. So let us begin. I'll just write it down for you. So, problems on indefinite integration. Okay, so for the first problem which we are going to solve is this: integral of minus 2x into sine of 1 minus x square dx. So what I want you to do is to try and pause the video for maybe minimum of 2 minutes to maximum of 10 minutes and figure out all the details yourself, and if you can just resume the video then. Otherwise I'm going to give you 10 seconds here and I will start it solving after 10 seconds. Okay, so firstly let us denote the integral by I, okay, as usual. So I is basically minus 2x into sine of 1 minus x square dx. Now, as we have learned in the previous sections, we are trying here to look for a term whose derivative is present so that we can substitute it for that. And you see a minus 2x dx present, and we note that the derivative, that is d dx of 1 minus x square, is just what we need because it is minus 2x dx. You can work out the derivative yourself because the term for 1 will be 0 and the term for minus x square would be minus 2x, right? So the dx won't be here because now we can set y equals to 1 minus x square, and then we can write dy equals to minus 2x dx, right? So dy is minus 2x dx and y is 1 minus x square, which we can substitute in the integral. So to get I equals to sine of y into dy, which we already know as minus cosine of y plus c, and we can substitute back the answer, which is minus cosine of 1 minus x square plus c, which is the answer for this integration. So I really hope this was not really a hard one, because considering the examples we have done in the previous lecture, so this would be solvable by most of you. Let us proceed to the next one, because this was just as an example where you need to substitute a single term to find out the answer. The next example would be something like evaluate integral of x cube into root over of x to the power 4 plus 2 dx. Right. So I'll give you again 10 seconds for you to solve it or have an idea of it, or if you want to solve it completely, please pause the video and take as much time as you can. Okay, so I hope you did solve the problem, or if you couldn't, you were stuck at some particular idea. If your idea actually was to substitute this term, it was correct, because we are going to do exactly that. What we are going to do is this. Let us denote. First, we denote the integral by some variable capital I, which is x cube into root over x to the power 4 plus 2 dx, and we set y equals to x to the power 4 plus 2, because when we differentiate both sides, what we get is dy equals to 4x cube dx, right? And we want the value for x cube dx here in terms of y. So therefore x cube dx is just dy by 4, and then the integral becomes I equals to integral of that thing becomes dy by 4, the x cube dx thing, and this becomes root over of y, right? So it's 1 by 4 into integral of root y dy. It's 1 by 4, and root y of dy is just y to the power 3 by 2 by 3 by 2 plus c, and this would be 2 by 3 into 4, which is basically 1 by 6. So the answer is 1 by 6 y to the power 3 by 2 plus c, and if you can substitute y back, the answer would become 1 by 6, and y was x to the power 4 by 2, so it's x to the power 4 plus 2 whole to the power 3 by 2 plus c, which is the answer for our integral. So this really are some of the easier integrals which we are trying to evaluate here, because it's just simple substitution and nothing much to find here. So we'll try to do some better problems. So let me introduce you to you the new concept, which is integration by parts rather, and then we can continue solving problems which are mixed from both the sections. So integral by part, which is also known as IBP in short. So as the name suggests, it is actually a rule to find out integrals of the form where you have two functions fx into gx dx. What we do here is we try to name or label the functions as function 1 or function 2, and once we do that, we can have an easier rule to find out the integral in terms of another integral, which might be easier to solve. So as of derivatives, it does not obviously give you a direct answer, but it rather gives you a newer integral which might be easier to solve, and we have a rule for it. The rule is something like this. The rule is called ILET. I for inverse functions, L for logarithmic functions, A for algebraic functions. Algebraic functions means function of polynomials like x cube, x to the power 4 plus 2 and something like that. Logarithmic is involving log, inverse is involving sin inverse x, cos inverse x, tan inverse x, like that. So they're inverse trigonometric functions. T is for only trigonometric, and E is for exponential. So why is this order important? This order is to choose the function that you choose is which is higher up the list, which is like if the function, there are two functions in multiplication form, which is one of them are inverse and another one is algebraic, then you would have the inverse function as the first function and the algebraic as the second function. So if the function is higher up on the list, you would name it as function 1 and the other one would be function 2. So let us name here fx as function 1 and gx as function 2. Then what it gives you is function 1 directly comes out into integral of function 2 dx minus integral of derivative of function 1 into integral of function 2 dx multiplied by derivative of function 1 and the integration of this whole. So this is how it works. So you take the first function and you multiply it by the integral of the second, and you subtract from it integral of derivative of the first function into integral of the second function. So let us take some examples so as to understand how this works. Example 1. Let us find out the derivative of x log x dx. Okay, so identify x is an algebraic function, right? ln x is logarithmic. So which one is more up the list? Obviously L, right? So L should be treated as the first function and x should be treated as second function. So denote the integral by I. Integral by I, and what we do get here is I equals to integral of x log x dx. Given that log x, we are denoting log x as first function, x as second function, which means we should have first function into integral of second function minus integral of derivative of first function, which is just 1 by x, into integral of second function and the integral of the whole thing, right? So integral of x dx is just x square by 2, right? So it should be x square ln x by 2 minus, we have already found the derivative for log of x, which is 1 by x, and again integral of x is x square by 2. So in this inner integral you do not need to include the constant plus c, so we are basically trying to just find the integral and accept the constant. So 1 by x into x square by 2 dx, and as we can see this becomes x square ln x by 2 minus integral of this x is cut off, it's x by 2 dx, which can also be evaluated because x square log of x by 2 minus this is x square by 2, so this is x square by 4. Now we can include a plus c to complete our answer. So x log x could not be evaluated otherwise. The only way is to guess the function whose derivative is x log x, which is kind of impossible. So we do not really need to follow that strategy, obviously, but this would give us the answer, right? Okay. So let us try to find out some more problems. For the next problem, what we do need is this: d dx of tan inverse x is equals to 1 by 1 plus x square. We are going to prove it, but first understand that since the derivative of tan inverse x is 1 by 1 plus x square, this also means that integration of 1 by 1 plus x square is equals to tan inverse x plus c. Okay, and how do we prove it? Okay, so let y equals to tan inverse of x, then what we see is x should be equal to tan of y, right? And what we are trying to find is dy by dx, so let us see how to find that. And the derivative of tan y is sec square y, if you remember it from the derivative section. So differentiating both sides, we get dx equals to sec square y dy, and sec square y is just 1 plus tan square y dy, and so dy by dx would be equals to 1 by 1 plus tan square y, but tan y is just x, so it is just 1 by 1 plus x square, right? So the derivative for tan inverse x, which is dy by dx, is 1 by 1 plus x square. Proving it, and all the other inverse functions can be proven in the same way, and corresponding to that we can find this integral. Evaluate integral of x to the power 4 by 1 plus x to the power 10 dx. Now at first glance, obviously that we want to eliminate or substitute for the denominator, but we see that the derivative of 1 plus 1 x to the power 10 is not x to the power 4 dx, right? Or not any constant multiple of x to the power 4 dx rather. But what we can do here is denote the integral by I then what we get is this: capital I is equals to integral of x to the power 4 dx divided by, and we can write x to the power 10 as x to the power 5 whole squared, because in that case what happens is, if we substitute y equals to x to the power 5, what we get is dy is equals to 5 into x to the power 4 dx, right? And what we want is the value of x to the power 4 dx. So therefore x to the power 4 dx should be equal to d of y by 5. So our integral becomes I equals to integral of, this thing becomes dy by 5 and the denominator just becomes 1 plus y square. So taking the constant outside, we get 1 by 5 dy plus 1 by y square. Now since we already know the derivative integral for 1 by 1 plus y square is tan inverse y, but if we hadn't known that, what we could have done is we can use trigonometrical substitutions in problems where we have something of the form 1 plus x square or 1 plus y square in the denominator or in the numerator. Because if you substitute, and remember, obviously you can make as many substitutions as you can. There is no rule of making only a single substitution for a single integral. As you can see, I am going to make a second substitution now. I am going to substitute for the substituted variable itself. So substitute y equals to tan theta, where theta is another variable. Then dy would be equals to sec square theta d theta, if you remember the derivative of tan theta, and sec square theta is just 1 plus tan square theta d theta, and as you know 1 plus tan square theta is just 1 plus y square d theta. So therefore taking this on the left hand side, we get dy by 1 plus y square equals to d theta. So this whole thing becomes d theta, right? So therefore I equals to integral of d theta by 5, and integral of d theta by 5 is just theta by 5 plus c. But theta, as you know, if y is tan theta, then theta would be tan inverse y. Then the answer would be tan inverse y by 5 plus c. But we also need to put back the value of y, which we substituted as x to the power 5. So the answer would be tan inverse x to the power 5 whole divided by 5 plus c, which is our answer, right? Okay, so this is another problem, and let us do another one. This one would be from the section of IBP. So obviously whenever you're facing, or you're in a situation where you are in exam or some problem solving session, you might not be given the topic, right? So you might have to figure out on your own how to do a certain problem of integration. If it's a definite integral, or even if it's an indefinite integral, you might have to substitute for something. You might have to do integration by parts. So there are various ways to do an integral, and you need to figure out which way works for you, which way actually solves the integral, because other ways might actually make you go round and round and come back to the same integrand again, right? So let us evaluate x sin x dx, and after that we'll do a more complicated version of this. So denote by I the integral, and whenever we see functions which are product of two different kinds of functions, we try to remember our eyelet rule, where we obviously know which one to take first function and which one to take second function. So in the eyelet rule, as you can see, eyelet, the algebraic function comes first after the trigonometric function. So algebraic function should be part 1, function 1, and the trigonometric one should be function 2, right? Then we have I equals to x into integral of sin x dx minus derivative of x, which is d dx of x, into integral of sin x dx, and whole thing is dx here, right? Now integral of sin x is minus cos x, so this is minus x cos x dx, minus x cos x, minus d dx of x is just 1, and integral of sin x is again minus cos x, right? Then as you can see, it simplifies considerably into minus x cos x, and this minus make it a plus, and 1 into cos x is cos x dx, and you do know the integral for cos x dx, which is just sin x, right? So the answer is x minus x cos x plus sin x plus c. So this integral is something which just comes back around its own, because the trigonometric functions, the sin x and cos x functions, generally they come back around its own when you integrate them enough number of times. So for example, they have a period of 4 on integration, so if you integrate sin x 4 times, you will actually get the same result. So let us try to find out something else here. Next problem would be integral of e to the power x sin x dx. Now this is a problem where you would know why the denote by integral I is of paramount importance. Okay, let's see. Denote the integral by I. Then what we have is I is equal to e to the power x sin x dx. Now if you remember in the rule I late, e, that is for exponential functions, that came last, so obviously e to the power x is going to be the second function here, and sin x is going to be the first function. So applying IBP, or applying integration by parts, what we have is this: I is equals to sin x into integral of e to the power x dx minus d dx of sin x into integral of e to the power x dx dx, right? So what we do get is integral of e to the power x is just e to the power x, so it becomes e to the power x sin x minus differentiation of sin x is cos x, so cos x into e to the power x dx. Now this is another integral, so again we apply the same integration by parts technique with cos x as the first function and e to the power x as the second function. Notice how we have to do integration by parts twice here, and we are doing it, as you will see why. It becomes cos of x into integration of e to the power x dx minus the integration of d dx of cos x, and as you know, integration of e to the power x dx is just e to the power x. I'll just write e to the power x dx here. So it becomes e to the power x sin x minus e to the power x cos x, and d dx of cos x is minus sin x, and minus becomes plus. It becomes e to the power x sin x dx, and if you take it away from the bracket, what becomes is e to the power x sin x minus e to the power x cos x minus integral of e to the power x sin x dx. But notice that this is the integral that we started with, right? So this is denoted by I, which is a variable. So this becomes e to the power x sin x minus e to the power x cos x minus I, and on the left hand side we have I. So solving for I, what we get, we get 2i equals to e to the power x sin x minus e to the power x cos x. Therefore I is equal to e to the power x whole into sin x minus cos x by 2, which obviously there is a plus c, which is the answer. So this is one of those integrals where you have to do integration by parts twice to get the answer. So this is a problem where we have basically the integral coming back on its own, and then we have to solve it like that. So this happens a lot of times. So let us do another problem. This one would be a bit tad harder than the last one because of the concepts involved. Evaluate integral of sine of log x plus cos of log x dx, right? Now obviously what we want to do here is, first, as this is not any function that we can be reminded of, this is not any elementary function, neither does it have substitution that is very clearly visible, so obviously the derivative of log x is also not present, right? So naturally the first thing we would like to try is to substitute for log x and see if that makes any difference, right? So obviously I is equals to integration of sine of log x plus cosine of log x dx, and substitute y equals to log x, which will give us dy equals to 1 by x dx, right? Therefore this integral would become, and from this you can see that dx is basically equal to dy into x, but we need it in terms of y, so x is basically e to the power y, so dx is basically e to the power y dy, right? So the integral becomes sine of y plus cos of y whole into e to the power y dy. And this is time to introduce a new theorem, or rather a lemma, which is helpful sometimes. So lemma: for a differentiable function f of x, if I is equal to integral of e to the power x into f of x plus f dash x dx, then the integral is I equals to e to the power x into fx plus c. So if you have an integral in this form, the answer is simply e to the power x into f of x. So the proof is necessary, so we shall do the proof here. We start with the integral, given integral, and we shall see why this lemma is important in solving this problem, this particular problem. So given integral is I equals to e to the power x whole into f of x plus f dash x dx. Now let us separate it into two different parts, that is e to the power x into f of x dx plus e to the power x into f prime of x, or derivative of fx dx. So let us try to break down this second integral. Name this integral as b. So b equals to integral of e to the power x into f prime x dx. If you apply integration by parts here with e to the power x as the first function and f dash x as the second function, what you do get is e to the power x into f dash x dx minus derivative of e to the power x is just e to the power x, and integral of f dash x, and then a dx outside, right? Now we know that the integral of a derivative is just the function itself, so it just becomes e to the power x into f of x minus this becomes integral of e to the power x into f of x dx, right? So if we put the value of b there, we see that I is equals to integral of e to the power x f of x dx plus b, where b is our desired integral which we have just evaluated using integration by parts, and which becomes e to the power x into f of x dx plus e to the power x into f of x minus integral of e to the power x into f of x dx. And as you can see, these two integrals cut off because they are exactly the same thing. So the answer is just e to the power x into f of x, which is the answer for the integral. Now in our given problem, in our given problem, we have I equals to integral of e to the power y, it was, into sine y plus cos y, right? So let f of y equals to sine of y, then f dashed y would be equals to cosine of y, and therefore I equals to e to the power y into f of y, which is sine of y, and cos y is the derivative, so f dashed y, right? And from the lemma we see that this is basically equals to e to the power y into f of y plus c. Putting back y, we get e to the power, and what was y again? Y was log of x, right? So we get e to the power ln x into f of ln x plus c. Now e to the power ln x is just x, and f of ln x is just sine of ln x plus c, which is the answer to our integral. So you see that this integral is found out using this law, and we can easily find out different integrals as well using this kind of lemmas whenever they're in the form of e to the power y into f of y plus f dashed y. So this completes some of the results that we might use. So in this video that would be all. So I will see you all in the next video, where we shall introduce some concept of definite integrals, and after that we shall finally move on to some solved problems for definite integrals, after which we can continue continuous random variables finally, because we might have a little bit of knowledge of integration by then to advance to those sections. So thank you again, and please do check out Breatter's Math app for more information, because all the theory and videos consulted in this lecture are also given in there. Thank you.